Good morning and welcome, good afternoon now. Good afternoon and welcome to the next chapter after circular functions, which is rates of change. This is a very, very short chapter which leads straight into chapter 17, which is the beginning of calculus. But first things first, we need to talk about the concept of rates of change. So when we talk about rates of change, we're talking about how a graph changes over time. And the way we do that is by looking at certain graphs. So for example, here I have what is this lovely thing here? Chemistry people, what is this? Bottle. What sort of bottle? There's a particular word I'm looking for it. It's not a beaker. It's a flask. There we go. That's what I'm looking for. Thank you. So this is a conical flask. It's a cross-section, obviously, because I'm not an artist. Now, as I am filling it up, the depth of the water increases. But if I were to plot the depth of that water over time, what would that graph look like? As I'm pouring that water into the flask, what would the depth of that water in relation to time look like as I am filling up? Is it going to be a shallow or a steep line? Over time, as I'm filling this in, so yes, the depth will increase as the time increases. However, say, will the rate of change here be different? So after a second, I only have this much. But after 2 seconds, I might suddenly have that much. And after 3 seconds, I might have that much. So what's going to happen is that the depth of water over time is slowly going to increase. But it's going to get, because there's less and less room. Because there's less and less room over time. And then when I get to here, the shape becomes constant. And then it becomes a straight line. And that's what we want you thinking about when you're completing these exercises. Is when you're looking at if you're looking at the shape of a vessel, the depth of the water is going to change and it's going to accelerate how much it's filling in that space of time. But then when it hits the straight bits in the middle, it's going to even out. So if I were to change the flask that I'm working with, so for example, if I just do a straight, so here is, there you go, there's a beaker. It's a consistent shape all the way. So if I were to fill that with this lovely green liquid, what would this graph, the depth versus time graph, look like? Is it going to look like this blue line? No. Ali, you've got it. It's linear. It's going to be straight linear because the rate of change, the rate of the volume change is going to be completely linear. The shape does not change. Now, let's flip this on its head. Let's flip this upside down. Let's say you are let's say you've got this weird bowl, a glass, a particular type of glass. It's a martini glass. Can't really hide that fact. if I'm filling this up, what's going to happen to the volume depth over time? Because it's gonna start filling. It's gonna fill from the bottom, and it's gonna be pretty consistent. But then, what is going to happen? Yeah, and then it's going to slow down. So it's going to start. It's going to start pretty consistent. But then how curved is it going to be? How curved is it going to be? Is it going to be like this? Or is it going to be like that? So, is it going to be the top line or the bottom line? So, is it going to be like line A or line B? A or B? All right, I'm seeing a mix of A's and a mix of B's. All right, so what I want you to do is I want you to think about it. The higher in the glass you go, the more you need to fill out a layer. So here there's not a lot before you can start adding on top of it. But when you get all the way up to the top, you need to go a long way. So I want you to think very carefully, A or B. The time it takes to increase the depth will increase, so it's going to slow down. So it's going to be, that's going to be an A-type graph. All right? It's going to have to be an A-type graph. So we'll do one more. Ooh, I got a good one. All right. It's a weird bottle. It's a very weird bottle. But go with me on this journey. What's the shape of this graph going to look like if I'm plotting the time versus the depth as I'm pouring this lovely green sludge into it? No, let's not go green. Let's go purple. Let's pour some purple in here. What's the shape of that going to look like? So Ali's got his first bit in, and I'm liking the way he's thinking there. So this bit here, that's going to be sort of linear over time. The ending is also going to be linear over time, but the question is, how do I join these two? This is going to be an accelerating. Well, this is going to be a decelerating curve, and this is going to be an accelerating curve. So what he suggested there is something like that, which is correct. This is exactly how I would describe it. The time it takes to fill slowly decelerates. Hourglass. Now you're talking my language. Now you're absolutely speaking my language. So let's... let's quickly fix that up. So and we will remove a little bit off the top there. So I'm going to pour some water in here. What's it going to look like? It's going to be an A line or a B line. Is it going to look like this or like that? All right, so it's going to start looking like a B and then become an A. So I'm just going to get rid of this so it's easier for us to see what's going on here. So over time, it's going to accelerate. Then it's going to have a nice straight bit there. So it's going to be linear for a little bit, and then the top is going to slowly it's going to decelerate, and it's going to level off here. All right. So I'm glad you guys get that. I'm glad some of you are able to get that and you're able to contribute, which is awesome. So one of the things that we're going to be doing, especially now that we're into the sort of calculus part of the year, is we're thinking about rates of change. And we're talking about gradients. And as you can see here, on this graph here, I have some curved lines and I have some straight lines. Those straight lines are constant gradients. Those gradients aren't changing over time. Whereas if you look at the first section and the second section, those are changing over time. And what we are going to be doing overall is looking at exactly how those gradients change from one point to another. So what we are doing today is this activity here, which is 16A. 16B is talking about constant rates of change, where the gradient of the line never changes. Basically a linear graph. And that should be pretty self-explanatory to you guys because we're in Unit 2 by now. If you don't know linear graphs, what are you doing? And then average rate of change. I'll get to that in a moment. The average rate of change, that formula that you see for there is going to look very, very familiar to you because it is literally y2 minus y1 over x2 minus x1, except it's written in function notation. All right. So, question there is, what if the container is circular? Well, I leave that as an exercise for you guys because I believe it is one of the questions in the book. And if it's not, I should tell them to put it in the book because it's an excellent question. No, it is not in the book. When you say it's circular, think about it. Well, let's do a quick example here. And then I'm going to set you guys on your way because I've been sitting at this computer since 8 a.m. and I need to get off. So I'm going to do my absolute worst impression of a circle. Unless there's a tool here to help me draw one. Is there a tool to help me draw one? Oh, look at that. It's got a helper tool for me. Excellent. So, if I am pouring a liquid into this, I'll make an opening at the top. Oh, what? Oh. I won't let me edit my little circle, but I like my circle. All right, fine. All right. Between here and here, what shape's that going to be? Is it going to be a fast accelerating curve or a slow accelerating curve? Because if you look at this, you have a little bit down here. It's going to go from here to here very quick, or very slowly. It's going to get slower and slower and slower until it gets to about here. At which point, it's going to go from decelerating to accelerating. Yes. So, I would say that the depth time graph is going to look something like this. Because over time, the rate slows down. Obviously, it's not going to be exactly like that. It's going to slow down over time till it gets to about here. So this point here in red, I wouldn't describe it as an inflection point because I'm pretty sure my graph shape is going to be wrong. But I'm sure there's a way you can model it, but that's outside the scope of what this class is about. So here is where it stops slowing down and starts accelerating again because we've reached the middle point of the sphere. And then it's going to accelerate again until it gets to the top, which is when it's up to here. But it's an excellent question, and I'm glad you've poked me about that, Ali. So 16A, B, and C are the exercises that we should be able to get through. I see you guys tomorrow, and by the end of tomorrow, we should be finished with 16A, B, and C. These exercises do not take that long.